putem începe. Stimați colegi, onorată asistență, astăzi avem onoarea de a audia prelegerea publică a colegului nostru, membru de onoare al Academiei de Științe a Moldovei și totodată colaborator al Institutului pentru Tehnologii Emergente al Institutului Leibniz de Cercetări Materialelor Stării condensate din Dresden, Germania și colaborator al Facultății de Fizice și Inginerie a Universității de Stat din Moldova. Prelegerea publică intitulată Inelul cuantic, un obiect și un domeniu unic pentru paradigma mecanicii cuantice și fizica topologică este prezentat în rezultatul unui ciclu larg de lucrări, de cercetări efectuate de către profesorul Vladimir FOMIN pe parcursul mai multor ani, care a fost dedicate investigării mecanismelor formării inelilor cuantice, proprietăților electrice, optice și magnetice determinate de topologie, dar și perspectivele de utilizare a acestor obiecte cuantice la elaborarea dispozitivelor electronice, spectronice, magnetice și diverse structuri dublu conectate. Totodată va fi lansată și monografia Fizica inelilor cuantice, care este tot rezultatul acestui ciclu larg de lucrări, și evenimentele acestea sunt dedicate celebrării Anului Internațional al Științei și Tehnologiei Cuantice 2025, care marchează 100 de ani de la dezvoltarea inițială a mecanicii cuantice. Vedem că acest an s-a încununat și cu un eveniment de mare învergură pentru acest domeniu, și anume ieri Academia Regală Suedeză de Știință a decis să acorde Premiul Nobel pentru Fizică 2025 profesorilor John Clark, Michael Devoret și John Martin din Statele Unite pentru experimentele care au pus în acțiune fizica cuantică, deschizând astfel noi căi de dezvoltare a tehnologiilor digitale. Deci este vorba de elaborarea unei noi generații de tehnologii cuantice care devin obișnuite pentru electronica largă. Savanții americani au efectuat experimente începând cu mijlocul anilor 80 prin elaborarea circuitelor electronice bazate pe materiale supraconductoare, demonstrând astfel că mecanica cuantică poate influența, beneficia viața de toate zilele. Celebrăm astăzi un secol de la fundarea mecanicii cuantice, dar totodată vedem că mecanica cuantică vine cu noi și noi surprize, și anume ceea ce a dus la oferirea acestui premiu Nobel în acest an. Mecanica cuantică devine baza tehnologiilor digitale, deschizând noi oportunități în criptografia cuantică, calculatoarele cuantice, senzorii cuantici. Îndeoseb, deci, calculatoarele cuantice promit capacități de procesare extrem de mari în comparație cu calculatoarele obișnuite, astfel că ceea ce ar putea efectua calculatoarele cuantice cu calculatoarele obișnuite ar necesita milioane de ani de procesare. Astfel, vă oferim cuvântul domnului Vladimir FOMIN pentru a ne aduce la cunoștință aceste cercetări elevate de obiectele numite inelele cuantice.
Mulțumesc frumos! Ok. Aha. Și laser nu funcționează. Foarte bine. И я хочу выразить искреннюю признательность президенту Тигеняну и руководителю секции, члену-корреспонденту Урсаки за приглашение на эту вот лекцию. Прежде всего, я хочу обратить ваше внимание на то, что эта лекция организована в рамках только что начавшегося научно-исследовательского проекта «Бридж» Национального агентства по науке и развитию Республики Молдова, который позволил мне быть здесь сегодня с вами. Как уже было отмечено, мы с вами находимся в необычном году. Это Международный год квантовой науки и техники. Коль скоро о нем уже было сказано, то я хочу вас просто поздравить с этим необыкновенным юбилейным годом. Но в этом году, в конце августа, вышла в свет книга «Physics of Quantum Rings», third edition, in Springer Nature. It accumulates the recent advances in the region of quantum ring physics over 6 years. This is not a reproduction of the previous edition. I think many of you know this previous edition, but this is a new book with new elements. And my intention today is to show you, to indicate some main stages in the development of physics of quantum rings with implications to current activities in the field of quantum science and technology. You see that the book is 621 pages. I was thinking about the appropriate format of my presentation. And some of colleagues whom I asked told that we are ready to follow you as long as you can. So I decided that I will speak as long as I will be able to stand here. And when I lose this ability, I will finish, okay? But maybe I will do it a little bit earlier. Look at the outline. I will start at some very early precursors of physics of quantum rings. Still before quantum era, and then there was a quantum dawn that fundamentals of topological effects will be shown. After fundamentals were established, there was a renaissance of quantum ring physics, and after that a long period of fluorescence which seems to continue till now. But I will be not able to speak about all achievements by all colleagues, even those who contributed to the last book. Therefore, I decided to speak about some recent scientific achievements which belong to my own scientific interest, and it will be vortex motion, rings of novel materials, advancement of theory. This field has wonderful perspectives. I have their multifaceted horizons, but I'm afraid there will be no time to speak about that. If you have special interest, please approach me after. Circular currents were prophetically introduced by Ampere as early as in 1820. I gave here some citations from the original work. I did not translate it, but you will easily recognize that speaking about magnetic materials, he wrote that there are electric currents around the poles of a magnet, and these currents are circulating. And what is a circulating current? Is anticipation of persistent currents, which I will introduce a little bit later. Quantum mechanics predicts that small enough rings or ring-like structures threaded by a magnetic flux in the equilibrium state carry currents. These currents are persistent, dissipationless. And these currents belong to the current state from, we all know quantum paradigm. Usually in ground state, there are no currents, but this is due to topology. You will see it soon. These currents do not require an external power source, but the prerequisite is that the electron state keeps quantum coherence over the whole doubly connected system. And this is why we are speaking about quantum rings. If we consider any ring, macroscopic ring, then coherence will be very easily lost. And if we do not have a unique quantum mechanical state in the whole ring, we will not have quantum interference. We will not have the specific phenomena which are at the basis of quantum ring physics. No good. I think I did it twice. Yeah. Still one. Yeah. It's very sensitive. The first interesting contribution was made by famous Linus Pauling, who was twice Nobel Prize laureate in physics and in chemistry. And he advanced a hypothesis that the external electrons in the benzene molecule can circulate freely and provide a very large contribution to the diamagnetic susceptibility when magnetic field is normal to the plane. So benzene is a molecule which is ring-like, you know. But he, from the very beginning of his studies, anticipated that in these regions, the potential function representing the interaction of an electron with the nuclei and other electrons in the molecule would be approximately cylindrically symmetrical with respect to the hexagonal axis of the benzene molecule, and the electron some distance above or below the plane of the nuclei are passing almost imperceptibly. This is a use, the word he was using, dissipationless. Current without dissipation. So look at the year, I think it's 36. Next to be mentioned is Fritz London. He demonstrated that the diamagnetic susceptibility of aromatic ring molecules was related to a current circulating around the opening induced by the magnetic field. And you can follow his citation. The current belonged to the ground state, and he concluded we can state that this dissipationless current flows without resistance, like in superconductors. He linked this emerging field of quantum rings to superconductivity. And the third very, very profound anticipation was made by Hund in 1938, who showed that at zero temperature, in thermodynamic equilibrium, even at temperature higher than zero, there existed a total current circulating around the annulus in a ring, which was dissipationless. And he already made an attempt to link it to some quantum mechanical ideas. Now, without mentioning other very interesting predecessors of the modern quantum ring physics, I like to emphasize that fundamental role of the ring topology for the quantum mechanical paradigm was shown within the theory of a geometric phase, some elements of which were stated by Rytov and Vladimir still before the war, Pancharatnam in 56 and Berry in 84. After Berry published his work, he was brought to the papers by Pancharatnam, and he agreed that, in fact, the first who rigorously demonstrated the existence of this geometric phase was Pancharatnam, though this phase historically bears the name of Berry phase. Now I give only a few formulas of the whole presentation. It's the only place which show how this geometric phase occurs. I am afraid that I will not be able to go in all details, but this is some very fundamental quantum mechanical problem with some constraints. So imagine that a quantum mechanical particle here for Gedanken experiment is put in a box, and this box is moved over some closed trajectory, for example, circular trajectory. And this is all maybe in some field, magnetic field, any field. One should solve then the Schrödinger equation. Here it has number 2, but both Hamiltonian and the wave function and the eigenenergy, they depend on the position of this box as a parameter. It's something beyond the first paragraph of the corresponding chapter in Landau and Lifshitz, because we have still additional parameter, external parameter. And when we solve this Schrödinger equation in general terms, this is last line, equation number 3, we obtain 2 contributions. One contribution is very common contribution. It's I, energy and time. But there is also another exponential. Unfortunately, I have no here a laser pointer, but look, after this dynamical phase, we have still something, another exponential. And this another exponential contains a quantity which is given here as a function of the wave function, But when we consider one period of this motion, it acquires the shape which is given here by equation number 5. So this is something which does not depend on time. It is not a standard quantum mechanical phase of a wave function. It's something additional. And this additional phase is called geometric phase. So I am trying here to show a very specific example. If we have a magnetic field and the particle is forced to move around some doubly connected contour, so it should be not necessarily a ring, but it can be something deformed, but it should be an object of a doubly connected topology, that at any 2 points in it can be joined either from one side or from another side, and these lines of connection cannot be transferred from one into another one by deformation. So doubly connected, 2 connections. Okay, and using the Dirac solution for a particle in a magnetic field, we arrive, it's so quick. I admire, this is very nice, quick, good, look. This phase acquires the shape which is given in the lowest equation. This is a ratio of the magnetic flux which is encircled by this contour to the magnetic flux quantum, which is nothing else but Planck's constant divided by elementary charge. So what we are speaking about, it's really a manifestation of quantum mechanical behavior, but under additional conditions which are imposed by topology. And because it's exponential, it's very clear that the dependence of the wave function, and therefore of any physical quantity which is calculated based on that wave function, are periodic in magnetic flux. And this periodicity is called, in modern terminology, Aronoff-Bohm effect, but we will go to it. Okay, this is a paper by Aronoff-Bohm, and the same like with Berry phase, there was another paper by Ehrenburg and Sidey 10 years earlier than Aronoff and Bohm published. They did not know about that paper, but these authors practically anticipated the effect of Aronoff-Bohm. But their work was not so widely known. And historically, the effect is called Aronoff-Bohm, though they, in subsequent papers, referred to the preceding paper by these authors. In fact, the whole story of quantum ring physics is in this one graph, which is taken from the first Aronoff and Bohm paper. We consider some electron beam to the left, which is split in 2, and then it circumvents the central part, solenoid, which condenses magnetic field. But in the area where the electrons move, there is no magnetic field. There is no Lorentz force which would act on electrons like a mechanical force. Then we will bring these 2 parts of the electron beam together, and in the place where they meet, we put a screen, if you like. The occurrence of the Berry phase inside this loop, which you see, now it's not a circle, it's a parallelogram, but it does not matter from the point of view of topology. Because the electrons in the upper part, in the lower part, acquire different phase. When they meet each other, they produce interference. And if you put at the point where they meet some screen, fluorescent screen, whatever is available in the experimental laboratory, you will be able to see a diffraction pattern. And that was soon after that confirmed experimentally. Again, unfortunately, I cannot tell now about everything, but I refer to the book if you are interested in these fundamental parts of the story. Electrons feel the vector potential in the region where the magnetic field is zero. This paradoxical effect is a direct consequence of quantum mechanical paradigm, because if the wave functions experience some modulation of the phase, they produce already visible consequences after they meet again. We can analyze now hundreds of different manifestations of Aronov-Bohm effect and similar Aronov-Cachet effect, where this geometric phase occurs due to spin-orbit coupling if you consider a spin-carrying particle, and they all, in fact, return to this fundamental picture of quantum mechanical manifestation of the change of phase. Okay? No? Good. So here I indicate a few early theoretical work, Byers and Young, 61, Bloch, 65, which showed as a solution of a theoretical problem that the magnetic flux through any surface whose boundary loop is entirely in superconductors and quantized in units flux quantum, where instead of elementary charge, which I showed, there should be double elementary charge, because Cooper pair consists of 2 electrons. This type of phenomenon, there are authors, Diver and Doll, simply by observing the diffraction pattern in a superconductor, observed the change in the period of this diffraction picture. It was twice different from that of electrons. And that was, in fact, the first experimental manifestation or demonstration of the fact that in superconductors, I speak certainly about conventional superconductors, the carriers of superconductivity are doubly charged. I think heuristical value of this demonstration can be hardly overestimated. It was done in rings, thanks to rings. Superconductors, good. But now I think the next picture requires a special emphasis, at least from my side. In two papers of 76 and 82, where together with Professor Brandt, the main actors were our Moldovan scientists, academician Ghițu, and Professor Nicolaeva, who is present here and whom I like to greet now especially. They considered the transport of bismuth whiskers. It's kind of cylinders. Cylinders are something which is singly connected, but in those whiskers, the currents were developing only, I would say, in the skin layer at the surface. So the area where the currents were flowing were doubly connected like rings. And they observed oscillations. Please look at the second panel here, but I admire it, that depending on the tilting angle between magnetic field applied and the axis of the whisker, because the area of loop was changing, the period of this transport phenomenon was just representing this change of area. For solid state doubly connected objects, it was a pioneering observation, and it is recognized in the literature on quantum rings. And I am especially happy that now I'm able to speak about this discovery, this participation of our Moldovan physicists within the general framework of quantum ring physics. I must go further. Okay, there were a few further experiments which brought into scientific implementation various types of rings. Again, now the number of such papers is extremely high, but I like to recall together with you three main papers which were in their sense the first. The first was the work by Levy and others, 1990, in an ensemble of copper rings. They saw very clearly Aronoff bomb effect in this ensemble. Second was a paper by Chandrasekhar from Evanston, who managed to fabricate a single ring, and he used highly sensitive miniature DC current squid in order to see again Aronoff bomb oscillations in this one ring already. So it was a tremendous progress from an ensemble of huge amount of rings, still a single ring. No, but it's, evidence is the increase of detecting ability. And the third here, Mai, 1993, who made gallium arsenic ring. For us, it might be more closer to us as traditional mainstream. Here was semiconductors, and he was able to make a single semiconductor ring. But how to measure what happens in it? He wanted to measure magnetization. Magnetization is in fact the same as current because they have the same origin. So this is different physical quantities, but the effect which is reflected through magnetization or transport current are similar. And he made something which really admired the community at that time. He made not only a ring, but also a squid in the same structure. So he growed in one run both quantum ring and the squid which was intended to measure the magnetization. Otherwise, it would be very, very challenging, if at least possible, to measure. And when he did it, it was really a long time work. He observed in the ballistic regime Aronoff bomb effect in the magnetic response, which was a fast detection of Aronoff bomb effect with this special technique. I'm very sorry, but here everything is very, very sensitive. It is good. I must adjust myself. There were very interesting theoretical problems which I sketchy represent here because there was a kind of discrepancy between existed then theory and experiments in what concerns, first of all, the magnitude of these Aronoff bomb oscillations, whether in current or in magnetization. And there was a concerted effort of different institutes and laboratories considering effects due to the finite size, disorder of different nature, and the electron-electron interaction. Here, very small deviation. The original work by Aronoff bomb and the subsequent papers which I mentioned, they were considering one-dimensional rings. But do they exist in nature? No. If you fabricate a ring, somehow it has width, which is not zero. It has height, which is not zero. There are inevitable impurities in it. And as a rule, there are many electrons which are interacting. And each of these aspects required development of very special theoretical approaches, which together allowed finally, but it took maybe 10 years or more to explain the observed height of these peaks in Aronoff bomb effect. It was not such an avenue which gave everything at once. It was a long and very intensive work. The contradiction between experiment in what concerns the magnitude has been recognized as a major open challenge in mesoscopic physics, and therefore it took big part in the monographs on mesoscopic physics, which were issued in the 90s and in the beginning of this millennium. A rigorous quantum mechanical theory of persistent currents developed for quantum rings in the ballistic regime revealed that the coupling between different channels of the electron motion in a ring caused the occurrence of high harmonics of the magnetic flux quantum in the persistent current, which also were observed experimentally. So I step by step introducing you into the real picture. If you measure it, you can rarely measure a single frequency. You should make Fourier analysis and then look what is the reason of the occurrence of other harmonics in magnetic flux. I wanted here to briefly indicate fundamental findings in the middle of 90s, but they have some personal flavor. After I was invited as Humboldt Research Fellow to Germany, I went to Halle, and at that moment appeared the first papers. The paper by Mailly was published in the same year when I came to Halle. Certainly, we were not able to go beyond this topic. And at that same moment, I started some direct research in this field. Allow me to attract your attention only to a few of these works. The first is the halving of the fundamental period may occur in a single finite width or finite height quantum ring due to the coupling of the azimuthal or radial electron motion by virtue of the impurity scattering. This was an experimental fact which was surprising, but it occurred that it can be tackled if you take into account the presence of impurities, which reduced the symmetry, but they did not reduce the topology. Therefore, there was persistent current, but not that like in an ideal rings. Second, the role of the electron-electron interaction in a finite width quantum ring again, with a sufficiently low density, at which the correlation energy is much larger than the Fermi energy, consisted in formation of an n-electron Wigner molecule with a relative angular motion of the electrons in the form of harmonic oscillations and radial motion depending on the shape of the confining potential. Simple terms. If you have 6 electrons in a ring, but that ring should be a finite width or finite height, realistic ring. The distribution of density will not be uniform. There remains something in quantum mechanics from classical behavior, which would have been if it were not quantum ring. But how would 6 electrons be distributed in a classical sense in a ring, taking into account their repulsion? They will form a hexagon in a ring. It will give you the lowest energy, true? but we are in a quantum world. The wave function will have some maxima and minima density of states, which will reproduce this hexagonal Wigner molecule in a ring. And then something beautiful happens. If you have this ring with Wigner molecule, then this Wigner molecule in a magnetic field will rotate because of Aronoff-Bohm effect. We are not aware of quantum interference, but this motion is dissipatively. This Wigner molecule rotates in a magnetic field without dissipating any energy. There are certainly other components of electronic motion. For example, radial, not azimuthal, but radial. And they interact with this motion of a Wigner molecule as a whole, and we get a complicated spectrum of absorption or photoluminescence or Raman scattering, which were analyzed just after that. And they significantly differ from those of free electrons in a quantum ring. So that the occurrence of electronic repulsion in a ring of a finite size cardinally changes optics of the system. Okay. On the basis of this previous stages, we must recall that the further progress in the field of quantum rings was mainly related to experimental advancements. And the cornerstone of high-tech industry in the beginning of this century was related to the creation of new fabrication technologies, new characterization instruments, and new theoretical insights. I must look at the time, still something. Because we arrived at fluorescence. I cannot jump over fluorescence. True? Look at this technological achievement, self-assembly through partial overgrowth. The previous rings were formed mainly lithographically, maybe one by one. Okay, if it's 10 million, it was different, but all other rings were individually done. And this work by Maillet took him maybe 3 years in order to grow this system. For any kind of potential applications, it's too cumbersome, too expensive, too long. But just at the edge of the new millennium, this paper by Garcia and others showed that you may grow indium arsenide quantum dots by solid source molecular beam epitaxy within Stransky-Krastanov growth mode. And after the growth of dots, some islands, some singly connected objects, they were covered with some additional layer. It can be indium, for example, and annealed after some time. To a surprise of this group, they observed such objects which are shown in the last panel. Here, you see, you all see it in front. And there are some holes inside. These are quantum rings, because the sizes are a few tens of nanometers. But they were grown in one run on the whole wafer. It was not a fabrication of individual ring, but it was a fabrication of an ensemble of rings. But I emphasize self-assembly. They were not controlling any of these rings. They were providing possibility for rings to grow everywhere. Okay, I think here in the center you see examples of profile. Upper two are quantum dots. Is a kind of curve with the maximum content of material. But after overgrowth, there is a minimum inside. What does it mean? That there is something doubly connected. It's ring. I must go further. And extremely interesting physical problem was treated by different groups, but two interpretations are standard. One, this group of Lorke and Kothaus, it's kinetic diffusion. The indium atoms, due to their high diffusion mobility at the surface of the compound, compared to the diffusion mobility of gallium atoms, for example, could diffuse out of the partially kept quantum dots, and they go to the surface and they gather there. The indium does not disappear, but it is redistributed, and it is redistributed in such a way that we get a ring. Another possibility, which is realized at some other conditions or for some other materials, is that thermodynamically driven de-wetting of the imbalance of surface and interface forces acting on the partially kept islands of indium arsenide gallium phosphide. What does it mean? You add this material which should give you quantum rings, and liquid droplets are formed on the top of the indium arsenide quantum dots, and that these droplets induce melting of the material of dots. It's thermodynamical already phenomenon, and due to this melting, the central part of a quantum dot goes out. We have again a quantum ring. There are also other mechanisms. I simply wanted to attract your attention because here is a nice combination of theorists and experimentalists, that this realm of physics really required a concerted action of people from different laboratories in the world and different specialities. Okay. Good. Now I go to another related topic. It's about advanced characterization of such rings. This is a part of development where I also participated. This is a top view on an ensemble of quantum rings. Look at them. First of all, they are not round. You see, they are elongated. If we are speaking about persistent currents, it's not good because the potential in which persistent current flows becomes non-uniform, and there are some obstacles. You can consider these parts in the apices of ellipses as kind of impurities. Okay. But what is in the center? Do you see black centers? What does it mean? What is in the center? That was the question. In order to answer that question, a very refined cross-sectional STM technology was used. You see here a few micrographs which show results of STM, but not from the top of a wafer, but we take a sample with rings and we break it. And then we do classical STM in another direction, from another side, which is usually not accessible. It was done in a statistically confident manner, and it brought such really astonishing results. These white or bright parts, these are elements which enhance content of indium in one direction and in another direction. Two crystallographic planes. First of all, there is certainly some reduction of indium content from the rim, from the ring itself to the center. I was asking you, but what is in the center? Yes, there is reduction of the content of indium, but there is not zero. You do not see a hole inside. The content of indium does not go to zero. It remains finite in one direction and in another direction. Certainly, the slope is different. We were able to characterize the shape of this ring very much in detail. I think on the next slide, you will see this theoretical model, which was derived from hundreds of such cross sections. It was a very nice work to reconstruct what is under the surface. But it's not zero. And okay. Yeah, it's again here. Yeah. This object is not a quantum ring. Quantum ring must be doubly connected. There must be an opening The theorem of Berry could not be demonstrated if there would be single connectedness. We see that these objects are singly connected. There should be no Aronow-Bohm effect because of that. It's a direct consequence of the derivation. No good. Colleagues continued their efforts. I can try to. And they observed. I will go just to the experiment. Yeah, here is the upper panel is the experiment. It's magnetization of an ensemble of such quantum objects. We call them quantum volcanoes because there is a rim and something in the center, which was obtained by torsion magnetometry in a magnetic field. Very small deviation of this wafer were detected by a laser which was 5 or 6 meters far from the object, but smallest motions of this wafer with quantum rings were confidently detected at such a big distance by reflection. You see oscillation on the experiment on the upper part. The derivation shows clearly a peak, and this is peak more or less corresponds to the position of the peak in a quantum ring. This was a big question. How can a singly connected object, quantum volcano, reveal a quantum interference effect in the shape of Aronow-Bohm oscillation, which should not be there? It was interesting. We made a rigorous theoretical calculation, including even strain in these volcanoes. And we calculated energy spectra. Look at the energy spectra. These are spectra which are very interesting. In a quantum ring, the ground state should be oscillating as a function of magnetic field. In a quantum dot, it should be revealing monotonicity. But in these objects, the ground state, for example, is represented by two oscillating states around some line which is monotonous. Why? This is because in such a structure, the electronic wave function has maxima in the rim and then exponentially decays to the center. In a singly connected object, which is called quantum volcano, I showed it to you, the electronic wave function is pertinent to doubly connected system, because if it exponentially decays, it's practically zero. It has no meaning to go into these exponentially small values. This conclusion allowed to resolve this paradox that you may have systems which are at the same time geometrically singly connected, and electronically doubly connected. Then we went certainly to excitons, to bi-electrons, and there are now many experimental work, including ongoing, which were explained in terms of this approach. I think I have already given you a flavor of quantum ring physics, and I really do not want to be blamed by doing it too much or too long. I can still stay here and I can continue. But if you allow me, I will briefly show you our very recent results, which might be equally interesting for you from general physical position. Yeah. There are other ways of fabrication of rings, and here is droplet epitaxy. Okay, you put some droplet and then you will etch it so that a cusp goes to a lower element, like in this right hand side picture. No time to go more in detail, but next, what happened there? Certainly lithography is one of the most popular ways to produce, to fabricate these rings. But lithography as such cannot make many rings. They can be of high quality, they are controllable, but they are unique, they are individual. This is an example. Yeah. In the meantime, people started fabricating rings of very different materials, including graphene and transition metal dichalcogenides. Why are they interesting? Because they combine two topologies. One is topology of the material, and another is doubly connected topology of this ring-like structure. And this combination of topologies is really a cornucopia of interesting physical effects, which even do not exist in these materials, which are called topological insulators, topological metals, topological superconductors. It's something more. We have an additional instrument to influence the energy spectra. And this is experiment in, I think, IPCO quantum rings, which revealed oscillations in magneto oscillations in magnetoresistance, which was also enigmatic. Usually in materials of standard or conventional energy band, this is explained in terms of little Parks oscillation. It's standard textbook, one of the beginning notions in superconductors. But in this case of high TC superconductors, it was not possible to explain the magnitude of oscillations. And relatively recently, together with my colleague from Napoli, we advanced such a picture which indicates the formation of vortices. It's superconductor, which can be represented in some equivalent way. but the resulting oscillation is due to quantum interference, like Aharonov-Bohm effect in rings which I was representing. And this allowed to decently explain the magnitudes of these oscillations and the background in one. Further, I think I cannot, yeah, maybe it's the last topic, but it's very, very recent topic. And I love it, and I want to tell you about it at least a little bit. This is a ring, simple, not quantum volcano ring, cylindrical ring. Imagine any wave which is spread in this ring. No, for example, in the cross section, which is in the upper panel. If it would have been 3D, then the wavelength would be any. But if it is such a confined object, and we have a certain direction of a wave, I repeat, any wave, there cannot be any wavelength. Why? Because there is confinement, and there cannot be wavelengths longer than this confinement. I think it has become already clear that if we will develop now any theory of superconductivity, and in this theory we must make a summation over the K-space. This summation cannot be done over three-dimensional K-space because of this limitation. Same in the cross-section. Look at the second graph. And one line, if a wave is propagating in this direction, it cannot have any arbitrary wavelengths, the same limit. And in the right-hand side, we indicated the allowed for waves areas in the K-space. It's very non-trivial. There are some voids which cannot be filled. They cannot be filled due to confinement. What of that? What of that? I think taking into account that in a ring of finite height and finite width, we have many such instances of confinement. We arrive at rather complicated pictures of allowed states, and they reveal transition between different homotopy groups. So these nice figures are classified by a special topological index, and you see that they are different. And then, taking into account this, we calculated within Bardeen-Cooper-like theory, but with restriction of the integration area, this behavior of the critical temperature. Yes. What is interesting here? First of all, that due to this effect, the critical temperature as a function of corresponding size is or might be non-monotonous. Look at upper two. or it can be monotonous, but lower not they consist of different stages, of different piece-wise continuous parts. I think you can see it better from your screens. So it occurs that there has been no systematic investigation of superconducting properties, very, very simple, critical temperature in quantum rings as a function of their sizes. And this is our prediction 2025. At recent conferences, I was attracting attention of colleagues, experimentalists, to try to see it. Certainly, one should not make too many, but one should check where is the maximum and whether there is no maximum if one changes another side. And now I have opportunity to attract the attention of our experimentalists, especially academician Sidorenko. Where is academician Sidorenko? But this is for him. We must see now together within our rebrain project whether there is or there is no non-monotonicity in the critical temperature of a quantum ring. Quantum ring remains forever. It's green. Okay. These applications also not only for rings, but for Möbius rings and for optical waveguides, which are ring-like, and for spintronics, and for magnetic nanorings with magnetic memory, which promise to be much smaller than planar magnetic memory elements. I must apologize. I already overdid it, and I just go to somewhere. These are my collaborations from many countries: Germany, Spain, Brazil, Italy, and I like to thank European Cost Action, where Moldova is represented, and I always give necessary information. And last year we had even a very nice cost action conference at the State University here in Moldova. And National Agency for Research and Development of the Republic of Moldova, which made my stay here possible. Thank you for your attention. This is a ring in cold gases.
Da, să mulțumim domnului profesor FOMIN pentru această lecție, această prelegere excepțională, dar și pentru dedicate fizicii inelilor cuantice, dar și pentru prezentarea din prima jumătate a zilei la cea de-a 7-a ediție a conferinței internaționale nanotehnologii și inginerie biomedicală, dedicată unui spectru mai larg de structuri cuantice topologice, ori complexitatea acestor structuri este demonstrată de faptul că doar una dintre aceste structuri, și anume inelele cuantice, pentru descrierea proprietăților a fost necesare de peste 600 de pagini în monografie recentă editată de Springer. Acum, dacă sunt întrebări...
Poate să felicităm.
După întrebări.
Domnul profesor, felicitări. Onorată asistență. Eu vreau să-mi permiteți să îl mulțumesc pe domnul academician, pe onoare, și să-i spun că în anul ăsta pizza de vie a rodit cel mai bine. Ia uitați-vă și struguri frumos. Da, mai ai aici. Asta e din recolta anului ăsta. Dar iată avem și din recolta anului trecut. Wow! Firma pe care o consult 10 ani la rând e Publică. Da, eu te rog frumos.
E o descoperire.
Domnul academician, vă rog frumos. Mersi frumos pentru tot ce dați-mi voi, vă rog, să vă îmbrățișez.
Cu plăcere.
Să vă mulțumesc.
Cu plăcere.
Să vă mulțumesc pentru tot ce faceți, pentru onoarea Academiei de Științe care
Eu sunt bucuros că am o posibilitate să fac ceva
Da, mulțumim. Dacă
utilă.
sunt întrebări, domnule Sala.
Ele astea cuantice pot fi aproximate ca de pol magnetic, de exemplu, să aibă un câmp magnetic pe el.
Da. Da.
Și dacă puneți un câmp exterior, el ocupat să interacționeze.
When we speak about magnetic materials, it's the only way. When we speak about other materials, we can calculate magnetic response, and then we will have automatically these properties of magnetic dipoles as a result. But I mentioned about these magnetic properties simply in the context of the overall development. My interests are in superconducting and semiconducting rings, not magnetic, but I know people who dedicated their experimental efforts to magnetic rings. So this is too a broad area in order to tell about everything, but in principle for magnetic materials, this is used.
На одном слайде вы показали ансамбль квантовых колец и в количестве 10 в 7 степени. Вопрос в том, что с одной стороны интенсивность квантово-механических эффектов вроде возрастает с количеством, а с другой стороны они должны быть очень идентичны. Как это возможно?
This was one of the first efforts, and they were not very identical, and they were not very uniform, and therefore the effect which was observed was not 10 to the power 9 higher than it was from 10 rings, because even the interference was spoiled. After that, with further developments, people started preparing rings which are more uniform in ensemble, but not of that work. It's already more recent work when people try even to make ordered rings. They can produce experimentally some super lattices, crystal lattices of rings, which are more or less identical and which are nicely arranged. And because of that, they achieve significant enhancement of the Aronoff-Bohm effect. But this is another story, not that work. In that work, it was simply an indication that Aronoff-Bohm effect exists.
Mai sunt întrebări? Da, domnul Țăuleanu.
Domnul profesor, scoate-le-mă.
Sigur că da.
Care sunt dimensiunile medii acelor efecte cuantice și cum se poate de regulat aceste dimensiuni?
Typical sizes of these self-assembled rings is 10 nanometers diameter. If you produce it by overgrowth, I take specific example for you. If you only start overgrowth, there will be a very bad ring with smaller opening. If you continue, the ring will be larger and deeper. So the geometry of ring can be regulated by the material of overgrowth, by the temperature of annealing, and by your patience, because if this annealing is performed within 1 hour, the quality of rings will be very bad.
And what is the diameter of cube of the ring? What is the diameter of cube of the ring?
Diameter
Of the cube of the ring.
But okay, if it is 10 nanometers, then you can have the opening maybe 6 nanometers, and then the ring will be 4 nanometers. It's all nano. But I finished this annealing. If you do it within 1 month, you will get rings of very high quality. But nobody has patience to wait such a time for that. So it's a compromise now. And the problem is not only the size, but the quality. They should be of high quality. In this sense, other methods which I mentioned, they are very, very promising. And certainly, if you take graphene, they are made lithographically. Lithography gives you high quality of rings. Depends on what is available and what are the goals. If you allow me, I return to this last slide because it's something nobody asked me. What means Alice ring?
I think
After I tell you,
Thank you.
Alice ring is a ring which is formed in cold gas after a monopole state of this cold gas is dissolved into a ring. And in the center there is ring. But this ring in cold gas has a very special property, and this is very recent paper. I like to reward you by your attention. If another monopole goes through this ring, it changes its sign. A monopole count is plus, and simply by moving through the ring, it becomes minus. This is just an effect which was observed by Alice in the Wonderland. He saw similar situations, not with monopoles, but with some animals. But this is now a reality. This is not a theory. This is an experiment. And in this sense, if you like to have some use of this effect, it's necessary to make them small enough, because in large it will not work. I understand your willingness to see some typical sizes, but different kinds of rings have different sizes and different heights. So everything depends on their demand. They can be fabricated on demand, but what is your demand? Then you will determine what should be the geometry.
Mai sunt întrebări? Nu sunt, deci mulțumim încă o dată domnului profesor FOMIN pentru această prezentare și să-i dorim succese în activitatea ulterioară și să-i spunem că îl așteptăm la Academie Științe și cu alte prelegeri a rezultatelor.
Mulțumesc frumos!